Ever wonder how Israel's Arrow 3 missile can destroy an incoming warhead traveling faster than a bullet? Anti-ballistic missile systems like Arrow 3 are engineered to intercept threats moving at several kilometers per second, using a mix of speed, precision, and advanced technology. But how does a missile chase and hit something barreling through space at hypersonic speed? Let's find out. In this video, we'll break down the technology behind these systems step by step, showing how threats are detected, tracked, and intercepted with split-second timing. To start, let's look inside the Arrow 3 and see what gives it the power to outrun and outmaneuver its target. If you're into advanced tech and defense systems, make sure to like the video and subscribe. There's a lot more coming. Powering the Arrow 3's flight is a two-stage rocket system designed for both raw acceleration and pinpoint control. The first stage is all about getting the missile moving fast. This solid propellant booster generates a huge burst of energy, launching the missile toward the upper atmosphere. Engineers tune the solid fuel mix for a stable, reliable burn, making sure the booster delivers just the right amount of thrust to escape the Earth's surface at incredible speed. Once this job is done, the booster detaches and falls away, having propelled the missile into the perfect position for the next phase. Now, the second stage kicks in. This stage uses a solid propellant sustainer rocket motor equipped with a thrust vectoring nozzle to fine-tune flight path adjustments. The sustainer motor keeps the missile moving at high velocity, but the real magic is in the nozzle. Like a submarine's thrust jets, the vectoring nozzle pivots to steer the missile in the vacuum of space, making quick, precise changes to its course. This is what allows the Arrow 3 to react to new radar information in real time, even if the initial targeting data wasn't perfect. The missile can launch before radar has locked in the exact intercept point, knowing it can adjust its path mid-flight as better data comes in. If you could watch this process in slow motion, you'd see the first stage peel away, spinning off as the second stage takes over. The nozzle at the back of the missile shifts ever so slightly, guiding the Arrow 3 through the upper atmosphere. These micro-adjustments might be almost invisible, but they're critical for making sure the missile lines up with its target, a warhead moving at several kilometers per second. Even a tiny delay or error could mean missing the intercept by miles. The real strength of this two-stage system is how it balances force and finesse. The first stage is all muscle, getting the missile up to speed. The second stage brings in the brains, using constant feedback to make sure the missile is always on track. Without this combination, the Arrow 3 wouldn't be able to cover the distance or make the fine course corrections needed to intercept a moving threat in the upper atmosphere. With brute power and surgical precision combined, let's see how the kill vehicle takes over for the final strike. Inside the Arrow 3 missile, the kill vehicle acts as the brain and final decision maker, responsible for intercepting targets at extreme altitudes. Deployed above the stratosphere, the kill vehicle handles the final interception far from ground clutter, where the margin for error is razor thin and reaction time is measured in milliseconds. The kill vehicle brings together three main systems: the propulsion unit with a thrust vectoring nozzle, a 150-kilogram directed high-explosive fragmentation warhead, and the seeker. Each component is critical for the vehicle's ability to make last-second adjustments, deliver precise force, and track a target that's moving at hypersonic speeds. First, the propulsion system. The kill vehicle uses its own solid rocket motor, equipped with a thrust vectoring nozzle that acts like a steering wheel, constantly nudging the vehicle's trajectory as new data comes in. This nozzle allows for quick, fine-tuned course corrections, so the kill vehicle can compensate for radar inaccuracies or sudden changes in the target's path. Compared to older systems that rely on side-mounted thrusters, this approach gives Arrow 3 faster and more flexible maneuvering, an advantage when every split second counts. Next is the warhead. Arrow 3's kill vehicle carries a 150-kilogram directed high-explosive fragmentation warhead engineered to focus its destructive power right where it's needed. Instead of simply exploding in all directions, this warhead directs its energy toward the intercept point, maximizing the chance of destroying the incoming threat while minimizing unnecessary debris. Its size and design are calculated to ensure that even hardened or shielded warheads are neutralized in a single strike. But the real intelligence comes from the seeker. This is the system's set of electro-optical sensors, which take over once the kill vehicle is closing in on its target. How can a tiny sensor head keep up with a target hurtling at miles per second? The secret lies in its 360-degree pivot mechanism. The seeker can swivel rapidly to keep the target in view, even if it's making unpredictable maneuvers or changing speed. This pivoting ability means the seeker doesn't have to move the entire missile to track the target. It can simply rotate its own sensor head, allowing for extreme lead pursuits and quick corrections. As the kill vehicle closes the distance, the seeker's electro-optical sensors lock on visually, distinguishing the warhead from decoys or debris. It fuses radar uplinks with onboard electro-optical data to refine its path in real time. This tight feedback loop means the kill vehicle is always reacting to the most current information, adjusting its flight path and seeker alignment up to the very last moment. The entire process is a coordinated dance of propulsion, sensing, and destructive force, all happening above the stratosphere and within a matter of seconds. Each system must function perfectly with the others, or the mission fails. This is the level of precision and adaptability required to intercept a threat traveling at several kilometers per second. So how does Arrow 3 and systems like it detect, track, and neutralize an incoming missile before it ever gets close to its target? Let's walk through the step-by-step process that brings all these advanced components together. The intercept process starts with relentless scanning by the Arrow 3 weapon system, always on the lookout for incoming threats. At the heart of this system is the Green Pine Phased Array Radar, a powerful sensor that sweeps the sky for objects moving at incredible speeds and altitudes. As soon as it detects a potential threat, the radar tracks its path, speed, and predicted impact point, sending all of this information straight to the Battle Management Center. Inside the Battle Management Center, things move fast. The system analyzes the radar's data, deciding if the incoming object is a real threat. If it is, the center calculates the best interception point and selects the Arrow 3 missile for the job. This decision has to be right the first time. There's no second chance. Once the intercept solution is set, the launch command goes out to the Arrow 3 launcher. The missile launches vertically, clearing the site in seconds. As it climbs, an aerodynamic stabilizer deploys just before booster burnout to keep the missile stable for that first sharp turn. The missile quickly redirects toward the calculated intercept point, adjusting its heading with precision. This rapid maneuvering is where the Arrow 3's agility shines, getting it on course to meet the target at the right spot and time. While the Arrow 3 races upward, the Green Pine Phased Array Radar keeps feeding it updated information. The radar tracks both the incoming warhead and the interceptor, sending real-time uplinks to refine the missile's trajectory. These constant updates let the Arrow 3 react to any unexpected changes in the target's flight path, like sudden bursts of speed or last-minute course shifts. Every small adjustment matters. At these speeds, even a minor error can mean missing the intercept by miles. But can radar guidance alone secure a hit? That's where the kill vehicle takes over. As the Arrow 3 nears the edge of the atmosphere, terminal guidance becomes critical. The kill vehicle separates, switching to its own electro-optical sensors for the final approach. This seeker pivots rapidly, tracking the target's every move and making split-second corrections. The thrust vectoring nozzle gives the kill vehicle the ability to steer with extreme precision, compensating for any last-minute data shifts or evasive maneuvers by the incoming warhead. In the final moments, the kill vehicle's sensors lock on visually, distinguishing the warhead from decoys or debris. The seeker's pivoting head allows it to maintain a fix on the target, even if it tries to dodge. The kill vehicle aligns itself perfectly, using its thrust vectoring to make the tiniest adjustments. Then, with everything lined up, it delivers its warhead right on target, destroying the threat high above the Earth. All of this happens in just a few seconds, from detection to destruction. Each part of the process, radar tracking, decision-making, missile launch, mid-course updates, and the kill vehicle's terminal guidance works together seamlessly. The result is a defense system that can protect entire regions from high-speed threats, relying on precision, speed, and coordination. With this level of engineering, Arrow 3 stands out as a major step forward in missile defense. Intercepting threats before they re-enter the atmosphere prevents any chance of hazardous dispersion, keeping civilian populations and infrastructure safe. Arrow 3's approach, neutralizing warheads above the stratosphere, adds a strong layer of protection to modern defense strategies. As new technologies emerge, the world of missile defense keeps changing. Could we see laser-based interceptors or AI-driven command centers next? Let me know your thoughts in the comments. If this peek under the hood of ABM Tech sparked questions, drop them below and subscribe for more engineering deep dives. There's always more to explore in the world of defense innovation.